Okay. Uh, someone asked me a question, okay? Um, we are spending so much time computing the RAM cohomology. Um, why are we doing that? So can you tell me a reason why it's a good thing to compute the RAM cohomology? Yeah. I think I said it at the beginning of the semester. Um, what do you think? Yeah, yeah, it's a way to distinguish between shapes or manifolds, right? So if two manifolds are diffeomorphic, then they should have the same de Rham cohomology. And so using de Rham cohomology, for example, you can prove that, a sphere is not diffeomorphic to a torus, right? So, yeah, yeah. So because their de Rham cohomologies are different. And that's the fundamental problem in any area of mathematics. In group theory, you want to tell, if two groups are isomorphic. In differential topology, the fundamental problem is to tell whether two manifolds are diffeomorphic. And the Ram cohomology is one way to do that. Okay, and so we have developed many different methods, and the last method was check cohomology. So it allows you to compute the Ram cohomology from the way open sets intersect in a good cover. Okay? Now, there's a problem with that. We have defined check cohomology only for an open cover, not for a manifold or a topological space. We know that if you have a good cover of a manifold, it will always give you the same answer, because when you use a good cover, the check cohomology is the Ram cohomology. Yeah, so it's independent of the good cover. But if you use other covers, you could get other answers. What we would like is a check cohomology for the space itself, not for a cover. Okay? And that's what we want to do today. Okay? Yeah, we want to see how we can get the check cohomology to be defined for a topological space, and not just for an open cover. Okay? And there's one fact that we used before, that I didn't prove, and that is that every manifold has a good cover. We assume that. But today, first, I would like to talk a little bit more about it to give some idea of why that's true. Okay? So we are going to start with the existence of a good cover on a manifold. Now, for this, you need some facts from differential geometry. I know many of you have studied differential geometry. So can you tell me what's a Riemannian manifold? A Riemannian manifold is a manifold, yeah, with a Riemannian metric. Good. And what's a Riemannian metric? That's right, yeah. So a Riemannian manifold is a manifold together with an inner product on the tangent space at the point for every point. Okay, so a Riemannian manifold is a manifold M with an inner product. Oh, and that inner product, it has to vary smoothly with a smoothly varying inner product on the tangent space, for all P in M. That's a Riemannian manifold. Now, an inner product allows you to talk about the length of vectors. And so if you have a Riemannian manifold, then you can talk about length. If you can talk about length, you can talk about angles, area, curvature, geodesics. Yeah? And so on a Riemannian manifold, so length and geodesics make sense. You can talk about what's straight, and a geodesic is a straight line on a Riemannian manifold. And so you can talk about a set being geodesically convex. Okay? So definition, a set in a Riemannian manifold is geodesically convex if, a convex set in the plane is a set so that any 2 points can be joined by a straight line. And geodesically convex means that any 2 points can be joined by a geodesic. If for all PQ in M, okay, there exists a geodesic joining P and Q. Or from P to Q. Right? Now, if you have 2 geodesically convex open sets, and you take their intersection, of course, it will still be geodesically convex, right? 2 points in the intersection will still be joined by a geodesic. Yeah. So the intersection of 2 geodesically convex open sets is geodesically convex. Okay? And now I need two theorems from differential geometry. The first one is that on a Riemannian manifold, every point has a neighborhood that's geodesically convex. On a Riemannian manifold, every point has a geodesically convex neighborhood. Hmm? And the other property is that a geodesically convex open set is diffeomorphic to Rn. Okay. Okay. So using these two facts, how can you get a good cover on a manifold? Oh, well, first of all, there's a theorem, fairly easy theorem. The first theorem in differential geometry is that every manifold can be given a Riemannian metric. So every manifold, that smoothly varying inner product is called the Riemannian metric. Every manifold can be made into a Riemannian manifold. Right? By giving it a Riemannian metric. Basically, it's because locally a manifold, is like an open subset of Rn, and so that has a Euclidean metric, and then you just patch them together with the partition of unity. Okay? And that will be a Riemannian metric on the manifold. Okay, so now let's say we have a manifold and I put a Riemannian metric on it so that it becomes a Riemannian manifold. How do you get a good cover? How do you get a good cover? Yeah. At every point, you take a geodesically convex neighborhood, and that will be diffeomorphic to Rn. And then if you intersect two of them, it's again geodesically convex. And so the intersection of any two is again diffeomorphic to Rn. And if you intersect three, well, that's like intersection two and then intersection, and take the intersection with another one, right? So any finite intersection will be geodesically convex and will be diffeomorphic to Rn, okay? So that gives us our theorem on the existence of a good cover. Okay, let's see. Let's put it here. Theorem. Every manifold M has a good cover. Proof. For every point in M, let's say UP be a geodesically convex neighborhood. then the collection of all these neighborhoods is a good cover. Yeah. Okay. Okay. Now, when you have open covers, there's this notion of a refinement. Okay? So that's another open cover, so that every open set, in this new cover is contained in some open set in the given cover. So, so for example, if you have like a cover like that, and, and say for every point, you take an open set in it, that would be a refinement. That's one way of getting a refinement. So an open cover say V beta refines U alpha. Oh, beta should be in B. If every V beta is contained in U alpha for some alpha. Okay. So you might think that, oh, well, then a refinement always has more open sets. Well, sometimes that's true, but it's not always true. And then, yeah, if V refines U, then we can also say that U is refined by V, right? So U is refined by V. And that we write as U is refined by V. Okay? Yeah. Yeah, every sentence with an act in the active voice can also be turned into a passive voice, right? Like uh-huh. So let me give you an example of a refinement. Well, here's an example, but here's another example. Let V, no, let V be open in X. X, V, and you let V be XV, okay? And U is just X. So does V refine U? Yes or no? Does V refine U? Is every open set in V in an open set in U? Yeah, yeah. X is in X, V is in X. Okay. And does U refine V? Does U refine V? Come on, it's just yes or no. Yes, yeah, because every open set in U is in V. So they refine each other. U and V refine each other, but they're not equal. Oh, um, excuse me, do you want to go to a conference on bifurcation? Yeah, it's in 505. Yeah.
说教室啊，
对对，你是要去一个那个 bifurcation 的会议，那个在505了。好，yeah. Okay. So U and V refine each other, but they are not equal. So that means refinement is not anti-symmetric. Okay. So refinement is not. Oh, what is that property called? Is it if A is less than or equal to B and B is less than or equal to A, then A equals B. Is that property called the anti-symmetry property or the symmetry property? I forget, but doesn't matter. I want to show you that a refinement is not necessarily a larger collection of open sets. Okay, yeah. Yeah, and you know, a refinement is specified by a map. When you are given a beta, you just need some alpha so that V beta is containing U alpha. Okay, so a refinement is given by a refinement map. Is specified by a refinement map. Okay, so if you have a refinement map, then for every beta, you have an alpha, okay, so that V beta is contained in U of phi of beta. So a refinement map tells you, yeah, which open set any V beta is contained in. Of course, it's not unique, right? This V beta can be contained in many different U alphas, but you just need one, one specification, okay? Then you get a refinement. And the next theorem I want to prove is that every open cover of M has a good refinement. Okay. So let's state the theorem. Every open cover of M has a good refinement. Can you think about how to prove it while I'm writing down the theorem? It's very easy. Theorem. Every open cover of a manifold M has a good refinement. A good refinement means that it's a good cover that refines you. Okay. Yeah. So of course, you want to first make this manifold a Riemannian manifold, and um, and so let's say you have an open set U alpha, okay, in the original cover. How do you refine it so that you get a good cover? I mean, you know that, well, you know what kind of open sets you have to use, right, in a good cover? So how would you do it? um, well, what kind of open set would you have to use to get a good cover? Geodesically convex open set. And so if I have a point P, what do I do to get a geodesically convex open set? I know that every point in a Riemannian manifold has a geodesically convex neighborhood. Okay? Now, but would that neighborhood be contained in U alpha? Hmm? If you look at P as a point of M, and you get a geodesically convex neighborhood, it might not be in U alpha. However, U alpha itself is a Riemannian manifold. An open subset of a Riemannian manifold inherits the same Riemannian metric. So U alpha equals a Riemannian manifold itself if M is. And so you can choose a geodesically convex neighborhood to be inside U alpha, okay? And in this way, you'll get a good cover that refines U, okay? So, yeah, so proof is that for P in U alpha, since U are, yeah, so, okay, so first of all, you make M into a Riemannian manifold, then any U alpha from this open set, open cover, is also a Riemannian manifold. And then for all P in U alpha, choose a geodesically convex neighborhood. UP contained in U alpha. Okay. Then, yeah, if you, okay, so this, yeah, this P depends on alpha. This UP is, it depends on alpha. Let's say UP alpha. So then all these, this collection where alpha is in A and P is in U alpha is a refinement, is a good cover that refines U. Okay? Yeah. All right. So that's enough about good covers. Okay. And now I want to just talk about some algebra. It's called a directed set. Yeah. So you see these open covers, you can talk about one open cover being refined by another, okay? So that's a binary relation, and it's transitive, right? If you have U, say V is refined by U, no, sorry, say U, start with U, and U is refined by V, and V is refined by W, right? Then U is refined by W, because every open set in U is in some open set here, and that open set is in some open set here, right? Yeah. So what property is that? Yeah, it's transitive. Okay? So refinement is transitive. It's also reflexive. Uh, yeah, an open cover refines itself. Oh, and then the other property, yeah, I think it's called antisymmetric. You know, if U refines V and V refines U, we know that it's not true, necessarily true, that U equals V. So refinement is not an equivalence relation. It's reflexive, transitive, but not antisymmetric. But it has another property. If you have two open covers, there is a common refinement. So how do you get the common refinement? So theorem, two open covers, U and B, have a common refinement. So a common refinement, is an open cover that refines both. And how would you get that? Let's say you have U alpha, V beta. What would be an open cover that refines both of them? Yeah, you just take all the pairwise intersections. So let W be the set of all U alpha intersect V beta, where alpha in A and beta in B. Okay? Then every intersection is in some U alpha and it's in some U V beta. And this will still be an open cover. Yeah, because every point P in the manifold it's in some U alpha and it's in some V beta, so it is in the intersection. Okay, so this then U is refined by W and V is refined by W. Okay? So if you think of refinement like as a binary relation, it's reflexive, transitive, and this property is called the upper bound property. Given any two open covers, there is one that is that refines both of them. Okay, so that's called the upper bound property. A set with these three properties is called a directed set. So a directed set is a set I with a binary relation such that it's reflexive, okay? So for all A in I, A is less than A. I probably should use less than or equal to, but anyway, this is shorter to write. It's transitive. Transitive means if A is less than B and B is less than C, then A is less than C, and then it has the upper bound property. And that means for all AB in I, there exists a C in I such that A is less than C and B is less than C. Okay, so one example is the set of all open covers of a manifold. I just realized that I was wearing a mask the whole time. Okay, now I think it's clearer. Next time I do that, please tell me. Yeah, okay. So the first example is the set of all open covers of a manifold. And tell me two other examples. Try to think of some binary relation that's reflexive, transitive, and has the upper bound property. Okay, so first example, the set of all open covers of a manifold M. Oh, well, it just needs to be a topological space, right? And then the relation is refinement. So that is a directed set. What's another example? Hmm? Yeah, the real numbers, the set of real numbers under which relation, under what? Less than? Well, it's less than reflexive. Yeah, it has to be less than or equal to, because it has to be reflexive. Okay? Yeah. Okay, so the first example is open covers and then refinement. And what's another example? Open sets and inclusions. So all the open sets of a topological space and inclusions. But when I write that, I actually mean, it doesn't have to be proper. Yeah, it's less than or included or equal to. Okay? But I usually write this to mean this. Yeah, so that's also a directed set. And so once you have a directed set, you can talk about a direct system of groups. You see, so, like when we have an open cover, then we can define the check complex, right? So C C star U. Oh, just a minute. Yeah, right. R. Yeah, so for every open cover, you get this check complex. And so you can look at all of these check complexes indexed by the open covers. Of a topological space. Right? I call that open X. Open X means, oh no, open X means all open sets. Yeah. So U is like open covers. Yeah. Now, all right. So for every open cover, you get a check complex, which is an abelian group, and oh yeah, right, yeah, and then like if one open cover refines another, there's a restriction map that we will define, so that this becomes what's called a direct system of groups. Okay, so direct system of groups, or it could be abelian groups or modules, whatever. A direct system of groups is a collection of groups indexed by a directed set I, such that, okay, for all A less than B in I, A less than B in I, there is a restriction map. No, just a minute. So, yeah. Yeah, for all less than B in I, yeah, there is a restriction map. There, there's a group homomorphism. F. Now, should I write A to B or B to I? B to A. A less than B. Okay, so then there's a group homomorphism from FAB from G of A to G of B, satisfying two properties. And you should think of it as a restriction map, okay? And so the two property is that F of AA is the identity on GA. Okay? And then if A is less than B is less than C, then you can restrict from A to C, and it is the same as first restricting to B and then restricting from B to C. Okay? So it satisfies these two properties. Okay, now, now do you think that there's another way to say this definition using categories and functors? Let's take a break and you think about what this is in terms of categories and functors. What is a direct system of groups? Okay, all right, let's take a break for 10 minutes. All right, yeah. Now, just now, during the break, two students came up to me and pointed out that what I said earlier wasn't true, that the intersection of two geodesically convex open set is geodesically convex. Okay? So there are two problems. Now, so one example is, is the cylinder, okay, where you cover it with two open sets. So that's U. And then V, you know, V would be like this. So in terms of a rectangle, okay, so U would be this open set. And V would be this part. The problem here, both of them are geodesically convex, but the intersection is disconnected. When a set is disconnected, then there's no way to join a point P here to a point Q there with any curve, you know? So yeah. So one problem is that, yeah, when UV are geodesically convex, U intersect V may still be disconnected, and if it's disconnected, then it's not geodesically convex. And then another problem is that when you have two geodesically convex open set, you know, it's just that it might be that the, you know, geodesics that join them do not lie in the intersection. So even though you have a geodesic in U that join these 2 points and a geodesic in V that join these 2 points, those geodesics may not lie in the intersection. Okay? Yeah. So what I said earlier wasn't true. So the geodesics, the geodesic joining PQ in the intersection uh-huh, uh-huh, PQ in U uh-huh, may not lie in the intersection. And same with V. And so there's no guarantee that you actually have a geodesic joining P and Q inside the intersection. Okay. Okay. So it's not true that the intersection of two geodesically convex open sets is geodesically convex. Yeah, so, but one of the students suggested a way to fix that, and that is you can't just take any geodesically convex open set. You have to take what's called a normal neighborhood. But let's not get into that. Okay, I can fix it, but I'm not gonna do it here on the blackboard right now. Okay, so yeah, it's not true that the intersection of two geodesically convex open set is geodesically convex, but you can still get a good cover by taking an open set that is geodesically convex and inside a normal neighborhood of a point. Okay? Yeah. So the theorem is still true, but I'll have to fix the proof. And I really appreciate that you bring these counterexamples to me. It's terrible that this is being filmed. I probably should delete this lecture. Yeah. Okay. So I've defined a directed set and a direct system of groups. And so let's see how the check cochains can give you a direct system of groups. Okay. Yeah. Okay. But first, let's when you have a direct system of groups, you can define what's called the direct limit. Okay. So the direct limit. So let GI be a direct system of groups indexed by a direct set I. Okay. So if A is less than B, then you have a group homomorphism from GA to GB. And maybe, maybe it goes to something else too, say GB prime. Okay? So we are going to define an equivalence relation on the disjoint union. So consider the disjoint union, okay? And we will define an equivalence relation on the disjoint union of GI for all I in I. Okay? You've got all these groups and you just put them together, but with no intersections. So you will say that A in GA and B in GB, so these will be elements in the disjoint union, are equivalent and you write A tilde B if they are eventually equal. Okay. Okay. Now A and B. Let me see. So they may not be related in any way, right? Because A and B need not be comparable, right? So so you have GA and GB. Mhm. But you know that there is a C that's greater than both A and B. They have an upper bound. Okay, so there exists as okay. So if for some C greater than A and greater than B, but we write it as less than. So some C that's greater than both of them, you know, you have a map FAC and a map FBC here. Oh, right. Oh, yeah. Let's see. So, oh yeah, right. That's right. Yeah, yeah. Thank you very much. So I should write GA and GB. Yeah, they're equivalent. GA is equivalent to GB. Uh-huh. If they are eventually equal, so that means when you go further down, you know, there's a C that's greater than both A and B. And so you have these two maps, FAC and FBC. And they become equal. Okay? Yeah. Okay. So you just think of it as GA and GB, they eventually become equal. Then they're equivalent. Okay? And then now the direct limit is this disjoint union where you identify all elements that eventually become equal. Okay? So you write it this way, the direct limit for all I in I of GI, by definition, it is this disjoint union marked out by the equivalence relation. Um, uh-huh. Now, this direct limit is still a group, okay? So the direct limit is a group with addition given by, well, an element in the direct limit, right, is the equivalence class of some GA. So let's say you want to add the class of GA and the class of GB, and what you do is you find this GC and then you push both of them forward. So then they are in the same group. And so you can add them. So you add FAC of GA and FBC of GB. And that will be an element of GC. So you can take its equivalence class. Okay. So it has, the direct limit has addition. Now you have to check that it's well defined because this definition depends on C. But yeah, it's easy to check that it will be well defined. Okay. So this is well defined. Okay. So now we want to go back to our check cochain. Yeah, so I want to show that the check cochains form a direct system of groups. And so that, yeah, we can eventually take the direct limit of check cohomology. So I would like to define the check cohomology of topological space. Yeah, you know, I probably won't get to the definition today, but we can go halfway. So let X be a topological space. And you have two open covers. U and V. And then we assume that U is refined by V, and it's given by a refinement map phi from B to A. Okay. Such that V beta is contained in U of phi of beta. Okay? So I want to define a restriction map. Okay, so we define a restriction map based on this refinement map, and it should go from the check complex of V okay. Now I can just use the locally constant sheaves, but why not use any pre-sheaf? Because it's exactly the same definition. So let F be a pre-sheaf on X. Okay? Then you can talk about the check complex with coefficients in F. I mean, that's going to be exactly the same definition, as when you use differential forms. This would be the product, direct product of F of U alpha 0 to alpha P, alpha 0 less than alpha P, right? So, this is V. Oh gosh, so I should use beta V. Right, that's the definition of the chain complex. And the restriction maps, you go to CPU of F. Okay. And so you start with some omega here, and then phi hatch of omega is an element here. So you need to give its components. Oh no, just a minute, is this right? Oh God, yeah. Okay, so yes, that's, I mean, I should start with U. Yeah, that's right. Yeah, if U is refined by V, then the arrow should go this way from U to V. Okay. This should be U, and this should be V. Because a direct system of groups, yeah, it's a covariant functor from the directed set to groups. So yeah, you should start with U and you go to V. So phi hatch of omega, okay, it's a chain in V, and that means you need to give its components. And you define it to be omega of phi of beta 0 to phi of beta P. Okay? Yeah, so this map, it depends on the refinement map. And there are many different ways of giving the refinement maps for the same refinement, but we have to show that, they give us the same answer, the same, well, what we have to show yeah, is that we don't really want a restriction in cochains, but we want a restriction in cohomology. And so the theorem is that this commutes with the differential so that it induces a map in cohomology. Okay? And then we take the direct limit of this direct system of groups, which are check cohomologies of open covers, and then we'll get the check cohomology of the topological space. But yeah, I'm going to stop here today and we'll continue next time. Okay.